This video is for our final project in AERO 320, Fundamentals of Dynamics and Control. For our project, we decided to describe the dynamic process of cruise control. The purpose of this cruise control system is to maintain a constant vehicle speed despite external disturbances, such as changes in wind drag or road grade. This is accomplished by measuring the vehicle speed, comparing it to the desired or reference speed, and automatically adjusting the throttle according to a control law. In order to understand this complex dynamic process, we decided to make a simplified model of a typical cruise control system that is in most modern vehicles. Shown here is a free body diagram of our system. Our mass, M, is a 2006 Acura TL. The mass is acted upon by control force U, which represents the force generated at the road tire interface. In order to simplify our model, we will neglect the internal dynamics of the vehicle, such as the powertrain, tires, and other factors that go into generating the control force. The resistive forces, BV, due to wind drag and rolling friction, are assumed to vary linearly with the vehicle velocity v and act in the direction opposite of the vehicle's motion. The reference frame for this system is a simple two-dimensional XY coordinate frame.
With these assumptions, we are left with a first-order mass damper system. Summing forces in the x direction and applying Newton's second law, we arrive at the following system equation. The forcing function that tracks how the car changes speed is u, the control force. U equals the mass times acceleration plus the damping coefficient multiplied by the current velocity. The input of the system is the current velocity of the vehicle, and the output of the system is the new velocity of the vehicle. Using the equations of motion, we were able to create the continuous state space model of the system. Then we did a Laplace transform of the governing differential equation, while assuming zero initial conditions to find the transfer function of the cruise control system to be 1 over ms plus b.
Now that we have defined our dynamic system, we will enter in some initial conditions. The mass of the car is 1,579.862 kilograms. We will assume a damping coefficient of 50 newton seconds per meter and a reference speed of 10 meters per second. Cruise SS creates a continuous time state space model of the governing equations. P cruise is a continuous transfer function model.
This is our plant model that we created using Simulink. The input represented by input U is a control force U. The sum block sums the forces acting on our system. 1 over m is the multiplier to change the force into acceleration, since the acceleration equals the forces divided by the mass from Newton's second law. Finally, the integrator changes the acceleration v dot into velocity v. The velocity is fed back using a closed loop system, and it is output at output v.
We will now implement a control law into our system. This system uses a PID controller, which stands for Proportional Integral Derivative Controller. A PID controller is a control loop feedback mechanism which continuously calculates an error value as the difference between the output velocity and our desired reference speed r. The step block is our initial values, and the scope displays the response of the system.
Finally, we wanted to meet the following performance requirements for our system: a rise time less than 5 seconds, an overshoot of less than 10%, and a steady state error of less than 2%. By experimenting with different values in the PID controller, we were able to gather the values seen in the table and the graph. Ultimately, we were able to show that the dynamic cruise control system is in fact stable when using our control law.
So there you have it, cruise control as a dynamic process. Thanks for listening.